Okay, so hi everyone. This is this is the second screencast that I just did because I just made the first one. You're not going to believe what happened. I was in the middle of doing the screencast, and then a couple of BC Part 2 students came in asking questions about Taylor and Maclaurin series. I had this completely long conversation with them that lasted about 20 minutes. All the while, I hadn't paused the screencast. And I thought, well, that's dumb. Now you're going to hear this whole conversation, so I had to redo it. Okay. This is what was in class today. I gave you this DiffyQ, and like I said, I'm going between the applied DiffyQ and just the straight up math DiffyQ. The applied DiffyQ stuff, I think, Jeannie, you said it was harder. It's actually easier. Applied DiffyQ is much easier. The math part of DiffyQ, I mean, it's kind of like vomitous in terms of learning different methods. But that's where I tend to be more comfortable. The applied DiffyQ stuff, well, to be fair, I have actually never taught the applied DiffyQ stuff, so that's kind of new for me too. So, all that to be said, thank you for your patience as I kind of go through that for the first time and trying to teach the applied stuff in a way that's not clumsy and topsy-turvy. Okay, the point here is I gave you this DiffyQ, and the most important point here is we triaged first, okay? You saw if it was separable, no. You saw if it was in standard form, no. You saw if this was exact, no. We tried to make it exact and saw that the integrating factors were just going to be arduous, okay? And the question is, then how do you deal with DiffyQs like this? I gave you a hint. I said, let x equals uy, and then I said, when you left class, when you're all saying, what is this called? What is this called? The method that I'm actually going to show you here is called the uy or vx sub method. And you're kind of seeing where the uy or vx sub method fits. Part of where it fits is when you've exhausted all the simpler methods. And you'll see what I mean by uy versus vx. Here I'm having you do an x equals uy sub. Okay? So, and I think you're leaving class, and someone said, what would dx be? Well, okay, that's the first step. When you solve for dx means the differential of x. The differential of x means the following. The partial derivative of x with respect to u times du, that's going to be y times du, plus the partial derivative with respect of x with respect to y, which would equal u dy. Okay? Now, one thing that I want to bring to your attention, and Eric and Oliver, was that you? I don't remember. They were asking, what does differential mean again? And I walked them back. And I said, remember back in the day, I defined a new term for you. When you look at the differential of some function, and let's say the function is composed of variables of a and b, by definition, the differential of a function a and b, and sometimes we've called this the differential of z being f. By definition, the differential of the function is the partial derivative of f with respect to one of the independent variables times dA plus df by dB times dB. Okay? And these mean the same thing here. I'm just going to make some room. Right? That's one way to write it. The other way that you've seen differential is if you have dz, where z is f of a, comma b, this could be written this way. The derivative of z with respect to a, dA, plus the derivative of z with respect to b, dB, right? Any way you swing that. That's how I know dx is y du plus u dy, because x here, after all, is a function of u comma y. Okay? Now, here's what we're going to do. Again, remember, we triaged, right? We're using this new method here, this new method being the uy sub. Okay, we'll call it the x equals uy sub. And I just happened to look in your text. Your text calls this the x equals vy sub. It's the same thing. Okay, everyone, whatever letter this is doesn't make a difference. It's just x equals vy, x equals qy. The point is, you are substituting x as a linear function of y. Okay, when you do that, here's what happens. x equals uy, dx equals y du u dy. What I'm going to do is, in this original differential equation, I'm going to replace x with uy and dx with y du plus u dy. Let's do that with me and see what happens. Okay, let's just do it preliminarily. When I do this, I get the following. I get u squared y squared plus y squared dx is y du plus u dy plus u squared y squared minus u y squared dy equals 0. Now, a simple woman would look at this and say, this is more disgusting than this. Okay, but we are not simple women or men. I want you to look at something. What I'm going to do is ask you to take this diffie q and please put it in standard differential form, as this diffie q is. In other words, I want you to gather all the like du terms, gather all the like dy terms, and put them, group them accordingly after, and this is key, so after you first kind of multiply out all the terms. So here you're going to have to FOIL, here you're going to have to distribute dy times this, okay, all this out. Yes, I know some of you are like groaning and moaning and rolling and such, but you know what, just stop and do it with me. All right, when I FOIL, okay, I get this, right? What I want to do is get all terms first, and I'm going to group. But notice something here. Something beautiful happens. Positive uy squared dy, negative uy squared dy. Those cancel out. I'm going to take a little glance here. None of the remaining are like terms. Now I'm going to write this diffie q in standard differential notation. I'll meet you there. And this is what I've got. Okay? Now, you look at this, and you may have looked at where we've come from, and you may not be impressed. But you know what? You should be. Because what we've just accomplished here is we've accomplished a new diffie q, which you would now triage and go through and say, okay, how would I solve this? And you'd possibly, or hopefully, no, you will, make the discovery that this is separable. Okay? Now, I'm going to ask you just to go ahead and properly separate the variables here in this separable diffie q, and then I'm going to talk about the method and why it works. Okay, so I'll meet you after you correctly separate. All right, and when you separate, here's what happens. This is me solving for dy dx, factoring out y cubed, simplifying, cleaning, boom, separable. Okay, I am not right now, boys and girls, we are not going to go ahead and solve for the solution for this differential equation. This left-hand side is easy to integrate. This right-hand side, not so much. You'd have to use decomposition by partial fractions, special case though, because the numerator is degree 2 and not monomial. The point I want to make is this, okay? Right now, for this new method of solving a diffie q, I want you to make a note to yourself, which is that we had a situation where we had a diffie q in standard differential notation. All of our other methods were either painful, arduous, or impossible. And we had this x equals uy substitution. Okay? Let's just talk about the math of what happens here. Notice something. When I substituted x equaling uy, specifically, I'm making the substitution x is a linear function of y. And even more specifically, x is a linear function of y where the coefficient, so to speak, is another function, okay? So what I'm doing is I'm saying, let's take that function x and rewrite it, x, as a product of two functions uy, okay? Keeping y linear, right? Because again, this is a linear function of y because y is raised to the degree 1. I guess you could also say that x is a linear function of u as well. But u was the other variable we invited into this relationship. The point is, this statement, and by extension, the differential dx, this is kind of the x equals uy. That is the move we made. And when you rewrite x as such, and then namely dx as such, what happens is you modify your diffie-q into a diffie-q that is separable, right? And then we solve the separable differential equation as follows. The question that you naturally have is, does this substitution x equals uy method work for all differential equations such that after triaging, it's not separable, it's non-exact, and when I think about what the integrating factor would be to make it exact, it's a vomitous mess. Your question really is, when does the x equals uy method work? Okay, and I'm going to tell you when. This method, x equals uy, all right, let me go over here for a second. The substitution, the x equals uy, or the y equals vx substitution, and you are naturally right to say, well, we didn't do an example with y equals vx as a substitution. You're right, we have not yet. And the natural question in class tomorrow is, given these two options to substitute, x equals uy or y equals vx, how do we know which way to go? I'll tell you that tomorrow too. Okay? The x equals uy or y equals vx substitution generates, or I should say creates, okay, creates a differential equation that is separable, okay, only, okay, because your natural question is, could I use this method all the time? And unfortunately, no. Only if the differential equation is what we call homogeneous. And this is where I know some of you are going to start pulling your eyebrows out. A differential equation being homogeneous here is completely different than the definition of homogeneous. I think it was in chapter 1. And what's really interesting is I just kind of looked in your book and there's like an asterisk and it says something like, a big asterisk, like, notice students will experience great discomfort by the fact that the word homogeneous means something completely different and unrelated than homogeneous in the early chapter. So your question is, okay, what's the definition of a homogeneous diffie-q? A diffie-q is homogeneous if the following is the case. Ready? A diffie-q is homogeneous if function m of xy and n of xy are both homogeneous functions of the same degree. Okay? And so, I know sometimes people hate when you define something, like you define the word homogeneous using the word homogeneous, and I might hear you. So let me now define what a homogeneous function is. Okay? F of, let's just say, x comma y is a homogeneous function, of degree alpha if the following is the case. Okay, are you ready? If oh goodness, I'm out of room. If f of tx comma ty equals t to the power of alpha times f of x comma y. Okay? Let me give you an example. Let's say, so let f of x equals, 3x squared plus 2y squared. Okay? Oh, that's f of x y, excuse me. F of x comma y. Okay, let f of x comma y. All right, let's check this. What is f of tx comma ty equal? Well, let's see. This becomes 3 times tx squared plus 2 times ty squared. And this equals 3t squared x squared plus 2t squared y squared. And I notice here I can factor the t squared out. T squared times 3x squared plus 2y squared. Now look over here, okay? Because f of tx comma ty just equals t to the second times f of xy, right? Do you see how this is this, okay? And this is this, okay? Therefore, okay, so, come on, okay, therefore, the function f of xy is a homogeneous function of degree 2. Okay? Maybe you're wondering, when would a function not be homogeneous? Okay. How about this one? How about if I said, let's see, let's try this one. Let this f of xy equals 3x squared plus y squared minus natural log of x. Okay? Go ahead and show that this function f of xy is not homogeneous. Okay, notice the question is, what would f of tx comma ty be? Here's f of tx comma ty, and you'll notice there is no way I could factor out a multiple of t, or a power of t, such that, I'll write this down, there is no way that I could factor out any value of t, let's call it t to the alpha, where I'd be left with just f of xy. Okay? So the fact that I cannot factor out any power of t and leave myself with f of xy as a factor means that f of xy is not a homogeneous function. Okay? So, this was a roundabout explanation to the question above. You said, you know, this method, x equals uy, the x equals uy method, will it always create a separable Diffie-Q? The answer is no. It will create a separable Diffie-Q only if the differential equation is called a homogeneous differential equation. A homogeneous differential equation is one where the function m and the function n are both homogeneous functions of the same degree. Now, you can go over here to the side and say, notice, function m and function n, I can eyeball it here, maybe you can too. They are both homogeneous functions of degree 2. If I had a Diffie-Q where m was a homogeneous function of, say, degree 5, and n was a homogeneous function of, like, degree 7, the fact that they're both homogeneous functions, but to different degrees, means that I cannot use the x equals uy sub-method. Okay? I call it the x equals uy sub-method. Now, here's the other question that I want to have for you too. When it's separable, right, we get down here, okay? When I separated, I was here. I kind of gave it away to you. This method is called x equals uy or y equals vx. Let's try this again with y equals vx, okay? Try this again with y equals vx, same Diffie-Q, okay? Y equals vx, and let's see which sub-method, x equals uy or y equals vx, yields a nicer, easier separable Diffie-Q. We know that either of these subs, x equals uy, namely linearizing x or linearizing y. Do you see how these are both the same methods essentially? Okay, linearizing x, linearizing y. Either of these will create a separable Diffie-Q, but are the two separable Diffie-Qs here equal in terms of their ease? Okay? So I'm going to have you just do that part. And I should say this too, the entire screencast here, this constitutes homework. There's nothing else added to this homework. And then tomorrow in class, what I'm going to do is build on this lesson. Okay, let's try the sub y equals vx instead of x equals uy. Okay, if you try the sub y equals vx, and again, remember, don't forget to triage. okay? In other words, one of the challenges about math is that, like in calculus, you learned partial fractions. Your homework was going to be on partial fractions, right? But on a quiz or a test, you have to know that you'll be given just a whole host of diffie-Qs each time, triage, okay? Let's try this y equals vx. Don't forget, you're going to want to also find the differential of dy to sub in. You do this sub, okay? Find the differential dy, and tell me at the end of the day, when you have your differential equations separated, which of the two was easier. I'll meet you there, do that now, and then check with me. Okay, look. See? This is all my substitution. Cleaning it up. Standard differential form. I know it's separable. Separate, separate, separate. And I know some of you were probably, lulled into a moment where you thought, this is going to be equally simple or equally complicated as my other one. And I'm going to very politely argue with you right now. Let's take a look at this. This is one diffie-Q. Here was the other one. Which one was simpler? Inarguable. Simpler. So, okay, simpler if I had to go and integrate. So here's my question to you, and this is the part where you're going to do some thinking. The x equals uy or the y equals vx method. My question to you is this: how do you know which variable to compose as a linear factor with the other? Or I should say this, let me rephrase. Which substitution, replacing x or replacing y? Replacing x in terms of y or y in terms of x? Do you see any connection between the original diffie-Q and the result between differential equations, one being simpler versus the other? I think a more succinct way to answer this question is, what is the connection you see between the relative complicated appearance of M versus N and your choice of choosing x equals uy or y equals vx? What is the relationship? If M is more complicated, M being the function attached to the differential dx, if M is more complicated, should you use x equals uy or y equals vx? If N is more complicated, N being the function that is a factor of dy, if N is more complicated, should you use x equals uy or y equals vx? And of course, I will ask you to come with your conclusion and the explanation of why. What is the relationship between M and N and the choice of x equals uy or y equals vx? And with that, I bid you good night.